I'm going to get started with Chapter 4. In Sections 4.1 and 4.2 deal with exponential functions. Okay? What is an exponential function? It is a function where a number is raised to a variable exponent. As you can see in the first example we're going to do together, a little base case here, 2 to the x power. So for the most part, you guys have been very used to variables to numerical powers, like x to the second, x to the third. This is the reverse of that. We have a number raised to a variable power, okay? We have a parent function for that, okay? A parent function, just be f of x is equal to b to the x power, where b is a real number. Okay. So there are some properties of an exponential function that we need to talk about. Okay? All exponential functions have horizontal asymptotes. Now the parent function here is really any number to the x power. So it's not even like a specific parent function. Okay? The horizontal asymptote of a parent function, 2 to the x, 3 to the x, 4 to the x, as long as there's nothing outside, nothing added or subtracted to the x, nothing added or subtracted to that term, will be at y equals 0. Let's talk about why that is. Okay, if I start plugging in numbers for exponents, positive variables, positive exponents, are going to make that number get bigger and bigger. Negative exponents don't make this term negative. Remember from Algebra 2, when you raise a number to a negative exponent, okay, it's just the reciprocal, okay? So for instance, 2 to the negative first is positive 1/2. It does not become negative, okay? Which means that there's no value for x we could plug in, or we're going to get a negative output, or an output of 0. It's going to get infinitely close to 0 as we plug in higher negative numbers, like negative 10, negative 20, negative 30. We'd have 1 over 2 to the 30th power. But it will never, ever touch 0. Okay? So the parent function has a horizontal asymptote at y equals 0. And as we talk about the transformations, that could move up and down depending on the function. Okay? It also, the parent function, has a y-intercept always at 0, 1. Why is that? Well, if you plug in a 0 for a variable in an exponent, anything to the 0 power is 1. So it doesn't even matter whether it's 2 to the x, 3 to the x, 4 to the x, 0, 1 will be on our graph. Okay? That's going to be important because we're going to want you and require you to be able to shift or transform this point and put it on any graph of future exponential functions. All right? What else might we require? We do some more points here. Okay? So let's start plugging in some values. We're going to plug in 2 values going away from the asymptote, or getting larger. So when x equals 1, y will equal 2. When x equals 2, y will equal 4. So we've got a 1, 2, a 2, 4. If we really wanted to get crazy, we could plug in x equals 3, we'd get y equals 8, and as you can see here, this graph will be growing exponentially. It's not linear. Okay? From one x to the next x, it's growing at a changing rate. It's growing exponentially. Okay? We could also plug in x equals negative 1, and for that we get a y of 1/2. Remember, 2 to the negative first power is 1/2. Okay, so we'll get infinitely close. Here is our graph. That is your first graph of an exponential function. That would be one of our parent functions, where we just have a number raised to an x power. Okay? This would be considered an exponential growth, because it's growing as x is increasing. Okay? If the b value is greater than 1, we would consider that an exponential growth. The opposite of that would be exponential decay. That would be if the b value is less than 1. I guess we should say between 0 and 1. A fractional b value, like 1/2. We would actually see it decay over time. It would be decreasing in an exponential way. Okay? So we have our parent function. We talked about a little bit of a graph here. We got some terminology down. Let's talk about the general exponential function. Okay? F of x is equal to a times b to the x minus c power plus b. Again, where b is a real number. These all do the same things that you would think it does based on transformations that you guys have learned in the past. Okay? Our a value would be a vertical stretch. Our c value would be a horizontal shift. And we think opposite of the sign. Our d value would be a vertical shift. It would follow the sign. Okay? That will help us graph. It will help us transform that one very special y-intercept, 0, 1, to the new point. It will also help us deal with the horizontal asymptote. Okay? So let's go ahead and take a look here at the second graph. Second example. We've got 3 times 2 to the x minus 1 power plus 3. First thing we're going to do is we're going to shift that parent y-intercept of 0, 1. Okay? And we need all of our functions here. We need our vertical stretch, we need our horizontal shift, and our vertical shift. The first thing we're going to do is multiply the y by 3. Then we are going to go to the right one. Then we are going to go up 3. Okay. So if we multiply the y by 3, because that's our stretch, this would move to 0, 3, right 1 and up 3 from there. So 0, 3, right 1, up 3. We're going to have a point at 1, 6. That's going to be a requirement for us for you to place on your graph to show us you understand these exponential functions. Okay? The next thing we might want to do is deal with the horizontal asymptote. The horizontal asymptote will be affected only by a vertical shift. It's not affected by a vertical stretch because it's normally at 0. 0 times anything would still be at 0. It won't be affected by a horizontal shift because a horizontal line is not affected by a horizontal shift. If it goes on forever left and right, in theory you can't move a horizontal line left and right. But it will be affected by our vertical shift of up 3, which means our horizontal asymptote will now be at y equals 3. We're going to require you on your graph to now plot 3 more points. 2 going away from the asymptote and 1 going towards the asymptote. So at x equals 2, x equals 2. 2 minus 1 is 1. 2 to the first is 2 times 3 is 6 plus 3 is 9. At x equals 3. 3 minus 1 is 2. 2 squared is 4. 4 times 3 is 12 plus 3 is 15. We're going to go off the graph here. Anytime we do that, may as well label it. And then we're going to plot 1 going towards the asymptote. So basically going to the left here. So at x equals 0, 0 minus 1 is negative 1. 2 to the negative first is 1/2. 3 times a half is 3 over 2. 3 over 2 plus 3 happens to be 9 over 2, or 4.5. That is the requirement. We now connect our dots. that would get you full credit for the graph of this exponential function. We'll also talk about domain and range here. The domain of this function, all the x values, it would go on forever to the left, and I know it's increasing very quickly, but it would go on forever to the right. The domain of any exponential function would be negative infinity to positive infinity, all real numbers. The range we need to think a little bit more about. Nothing below 3, can't include 3, everything above 3. So we're looking from 3 to infinity for the range of this function. All right, cool. Well, we're going to save number 3 for another time. We're going to get to what we call the exponential. The natural exponential number, that happens to be the number e. Okay, just like pi is a number, e is also a number. Pi, dealing with circles, e dealing with exponential growth. What is e? This is e. Okay? As you can see here, as this function, the exponential function, which you'll learn a little bit more about when we get into some of these application problems, as n gets larger here, as n gets to 10 or 100 or 1,000 or 1,000,000, okay, as you can see here, or 100,000, this approaches a certain figure, just like pi approaches a certain number, okay? E has a value of 2.71827, and it would continue on forever. It is an irrational number. Okay, similar to pi, they calculate multiple, many decimal points of E. Okay? Uses of E. One of the main uses of E is in compound interest. Okay? In exponential growth models, like maybe populations. Okay? So lots of different uses of E that you will end up seeing. For us, at least in this first section, we just treat E like any other number. Okay? So just because we're going to graph 3 times E to the 0.5x, doesn't mean we're not going to treat it just like any other number. Okay? So, we're going to graph this the same way. We're going to shift that parent y-intercept of 0, 1. What will affect it? We're going to multiply the y's by 3. Okay? This horizontal stretch of 0.5, that wouldn't affect this. Technically, we would divide the x-coordinate by 0.5. Right? However, the x-coordinate already is 0. So any horizontal stretch here would not affect this shifted point. So we're just going to multiply the y's by 3, we get 0, 3. Okay? If you don't believe me, plug in a 0 there. 0 times 0.5 is 0. E to the 0 is 1. 3 times 1 is 3. Okay? Our horizontal asymptote would only be affected by a vertical shift. We don't have a vertical shift. So our horizontal asymptote will still be at y equals 0. And now we need 2 points going away, 1 point going toward the graph. So we plug in x equals 1. For x equals 1, y would equal 3e to the 1/2, or 3 over 3, the square root of e. Okay. We plug that into our calculator, we get 4.94-ish. So 1 comma 4.94. Okay. At x equals 2, y would equal 3 times e. We put that into our calculator, we get 8.15. Then we'll plug in x equals -1. We get y equals 1.81. And we are done.